This is a combination of type 1 and type 2. In other words, some physical law involves a variation inversely of a certain variable and directly of another variable. Volume varies as the temperature, actually absolute temperature. If you're wondering what that means, you might ask your science teacher. And inversely as the pressure. If you increase the temperature of this physical object, air in it will expand, pushing the piston out. In other words, as the temperature increases in value, so does the volume increase in value. So that's a direct variation. But on the other hand, at the same time, if you apply pressure to decrease the volume, then the pressure values increase, which is going in the opposite direction. So therefore, the physical law states that volume varies as the absolute temperature and inversely as the pressure. Let's use variables to represent these quantities. If V is the volume and T is the absolute temperature and P is the pressure, then the formula which represents this physical law is V equals K, always a constant of proportionality, varies directly as T, but inversely as P. I will now solve some variation problems. In the applications that follow, initial conditions will be given, which are the measurements of each variable in the formula. Except for K, of course. Refer to these as initial conditions. In my previous example, dealing with distance and time, the numbers given were initial conditions. The initial conditions allow you to solve for K. Rewrite the formula with the K value entered. New conditions, or sometimes referred to as final conditions, will be given regarding the variables except for one of them. which will be solved for. You will always have enough information to calculate that unknown variable. The method of solving variation problems just described is sometimes called the equation method. Another popular method that I will not introduce uses proportions. For example, after brakes are applied to a car, the distance it goes before stopping varies as the square of the speed of the car. Identify the statement or phrase of variability. It is here. Varies as. Identify the variables which the statement of variability connects. And they are: the distance varies as the square of the speed. In that statement, then, which is written as an English sentence, is a physical law, and it can be translated into a formula. Let us continue with the question. For a car going 30 kilometers per hour, the stopping distance is 12 meters. A, what is the stopping distance of the same car going 100 kilometers per hour? B, what is its speed if it takes 200 meters to stop? Begin by writing the formula. Let S represent distance in and V represent speed in the unit of measure kilometers per hour. Therefore, S is equal to K. Now it says the speed is squared. The square of speed is V squared, like that. That formula interprets, in mathematical language, that English sentence regarding a physical law. The first thing we must do is to solve for K. And solving for K can be determined, can be done by using the initial conditions, which this is. From this we see that therefore K is equal to S over V squared, which equals S is equal to 12 divided by 30 squared. You can work that down to a single number if you want to. It happens to equal, using my calculator, approximately 0.013 repeated. Supposing we reduce this to a fraction, and I will go down here like this, that would be 12 over 30 times 30. That becomes 4 over 10, or 1 over 75. Use the value for k now to rewrite the given formula. S equals 1 over 75 times v squared. There's the formula using the initial conditions. You use this formula now with the constant of variation in it to deal with the final conditions or new conditions. The new conditions are that the speed is 100 kilometers per hour. There are only two variables involved in the formula, so only one of these will be given and the other will have to be found. So for part A, S is equal to 1 over 75 multiplied by 100 squared. That amounts to 133.3 repeated. On the other hand, in B, starting again with the formula S equals 1 over 75 times v squared, we want to know what the speed v is if it takes 200 meters to stop. So we put 200 here where S is, 1 over 75 multiplied by v squared. It appears that v squared is equal to 200 times 75, which is equal to 15,000. V is then the square root of 15,000. And finally, V is equal to 122.47 approximately kilometers per hour. The amount of heat received by a body varies inversely as the square of the distance from a source. By a body or object varies inversely as the square of the distance from a source. How many times as much heat will be received if the body is moved to a point? How many times as much heat is received if a body is moved to a point A, twice as far, B, 1/3 as far, and C, 4/3 as far. The first thing to do is to translate this English sentence regarding a physical law into a formula. Find the statement that connects the variables in a variability, and it is varies inversely as. What are the variables themselves? It is the amount of heat and the square of the distance. This becomes the following. Let H represent amount of heat, no units are given, and S the distance. Then the formula is H equals K over S squared, square of the distance, S squared. There's your formula. We must solve for K, and K is equal to H times S squared. You look at this problem, and there are no numbers given as such for initial conditions. For example, what is the actual initial value for H? What is the number representing it? And what is that distance? Is there a distance given? The answer is no. So what you'll have to do here is assume initial conditions is in the following way. Let the initial conditions, I'll use COND for short, be H1 and S1. The subscripts indicate that those are numbers. Well, if those are numbers, the next step is to calculate the constant of variability, the constant K. So let's solve for K using H1 and S1. Therefore, K is equal to H1 times S1 squared. Use this value for K in the given formula. H is equal to H1 S1 squared, that's K, divided by S squared. That is the formula based on the initial conditions given or assumed. So this now represents the formula between heat and distance with the value of K in it. Now, what are the final or new conditions? The new condition is that how many times as much heat is received? That's the problem. How much heat is received if the body is moved twice as far from its original place? We assumed S1 is a certain distance. So twice as far is 2S1. In other words, S here, the S of this formula, is twice as far as in the initial conditions. We can now solve for H. H is unknown and will equal to H1 S1 squared over S is 2S1 quantity squared. That is equal to H equal to H1 S1 squared over 4S1 squared. Now look at what we have here. We have a fraction in which S1 squared is located there, and that can be canceled because between them that equals 1. Our final result is therefore that H is equal to 1/4 of the initial value for H, H1. For B part, the procedure is pretty much the same. You're given the formula to start with, you solve for K, you assume initial values, you then solve for K and replace for K those quantities. And then the formula is repeated with K a number. But now the distance is a third as far as before. A third as far instead of twice as far makes this 1/3 as far as the initial value. So we have to work with that now, and we're going to remove this and continue with the solution at that point. In other words, S, the new condition is replaced by 1/3 the old condition, or the initial ones. We therefore write that H is equal to H1 S1 squared, that's the constant of proportionality, over 1/3 S1 quantity squared. That amounts to H1 S1 squared over 1/9 S1 squared. Notice that, again, I have S1 squared there and S1 squared there. And simplifying my result, I would write that H finally is equal to 9 times H1. In other words, the new condition, or final condition, is equal to 9 times the initial condition when the body is moved 1/3 of the original distance closer. And now for part C, 4/3 as far, we simply have to change this part. And begin again. 4/3 as far will be 4/3 of S1. Consequently, H, continuing from here, is H1 S1 squared over 4/3 S1 quantity squared, and that's equal to H1 S1 squared over 16/9 of S1 squared. S1 and S1 cancel, simplifying and writing the answer out. Finally, we have that H is equal to 9/16 of in H1, the initial condition for the amount of heat.